hydrogen atom in its ground state is excited by means of a monochromatic radiation of wavelength 970.6 angstrom. How many different wavelengths are possible in the resulting emission spectrum? Find the largest wavelength among these. So let's understand with respect to the energy level diagram. Okay, so we find hydrogen atom in its ground state, and for ground state n equals 1. Okay, so this is ground state, and as in the question, okay, hydrogen atom is in the ground state. So we have this. So we have this, okay, and so we have this. Now what we find, hydrogen atom in its ground state is excited by monochromatic radiation. So we know monochromatic mean light or radiation having single wavelength, okay, having single wavelength. So this is to be noted, okay. So we have monochromatic radiation of wavelength 970.6 angstrom, and the energy of this monochromatic radiation is delta E, and we know this equals Planck's constant times frequency, and we can write in this way also, h times c, okay, divided by lambda, where c is the speed of radiation or speed of light, okay. So we have this. Clear? Now we need to find the energy of the incident monochromatic radiation, okay. So let us find the energy, okay. Energy of incident photon, okay. So I'm writing in short, okay, is delta E, and this equals hc by lambda. So we have this. Clear? And we can write in this way, okay, in SI system. Therefore, energy, okay, delta E of incident radiation equals Planck's constant, and we know Planck's constant is 6.63 times 10 power minus 34 joules second, and C is 3 times 10 power 8 meter per second divided by wavelength lambda, okay. So it is 970.6 times 10 power minus 10 meter. So we have this. So second and second cancels out, okay, or let me do in this way, okay. This cancels out, meter and meter cancels out, so we get energy of incident radiation or photon, okay, equals, after calculation we get this 2.04, okay, 9 times 10 power minus 18 joule. So we have this. So this is the energy of incident radiation in joule, and we know 1 electron volt equals 1.6 times 10 power minus 19 joule, okay. So we are going to change this energy in terms of electron volt. So we can write delta E equals 2.049 times 10 power minus 18 divided by 1.6 times 10 power minus 19 electron volt. So after doing calculation, okay, the energy of incident radiation or photon delta E equals 12.80 electron volt. So this is the energy of incident radiation or photon in electron volt. So we have this, okay. Now what we need to find is that we have to find the energy of the excited state. We know hydrogen atom is excited to higher state, okay, and we need to find the principal quantum number corresponding to the final excited state, and we need to find the energy corresponding to the final excited state. So I'm writing over here, okay. What we need to do, we have to find the energy of the final, okay, or excited state. So we have to find this, and we must find n, that is principal quantum number corresponding to the final state or excited state. So in order to find the energy of the final excited state, we use this expression, okay. We know due to this energy of incident radiation, hydrogen atom is excited to the final state. So we can write in this way, okay. We know delta E, okay, this is energy of incident photon. So this equals EF minus EI. So we have this. And what is EI, okay? So this is energy corresponding to initial or ground state, okay? So this is for initial or ground state. And what is EF? So EF, this is energy corresponding to final or excited state. So we have this. Okay. Now we know delta E, okay, equals 12.80 electron volt. Okay. So therefore we can write 12.80 electron volt equals EF minus EI. And what is the energy of ground state of hydrogen atom? We know energy of ground state of hydrogen atom is minus 13.6 electron volt. Okay, so we can write minus 13.6 electron volt. So we have this. Now let us do calculation. Okay. Therefore, we can write EF equals 12.80 electron volt minus 13.6 electron volt. So EF equals, we get minus 0.6 0.79 electron volt. So this is the energy of the excited state. So this is the energy, okay, of the excited state. Sorry. So we have this. Now we need to find N. Okay, we have to find this. So this is to be noted. Okay, now in order to find N, okay, to find N, we use this, or let me write in this way, for the excited state. Okay, we use this expression of hydrogen atom, okay, energy of the nth state. So what is this? This is energy of nth state. So this equals minus 13.6 electron volt by n square. So we have this. Here we have this. Therefore, we can write, since the energy of the excited state, okay, is minus 0.79. So we have this. So this is to be noted, okay. So we can write in this way, okay. EF equals, En equals minus 13.6 electron volt by n square. So we can write energy of the final or excited state equals minus 13.6 electron volt by n square, and this energy is, we know, minus 0.79. okay, this is minus 0.79, minus 0.79 electron volt equals minus 13.6 electron volt by n square. So let's simplify, okay, electron volt cancels. Therefore we can write n square equals 13.6 divided by 0.79. So n equals under root 13.6 divided by 0.79. okay, so we get n equals 4.1. Now, okay, we have this. So what we do is that we write, or we take n equals 4, okay, approximately. So we take this. I'm writing in short, okay. We take n equals 4. Clear? Now what we do is that, okay, we have this n equals 1 ground state, n equals 2, n equals 3, and the excited state is n equals 4. okay, so this is the final state or excited state. So what you find is that we get this, that is, hydrogen atom gets excited from ground state to n equals 4. okay, so it gets excited from n equals 1 to n equals 4. So we have this. Now we are asked to find how many different wavelengths are possible. Okay, so we have to find the number of wavelength possible. Okay, now what we find is that, okay, hydrogen atom is excited from ground state to this. Okay, it is excited from ground state to this, from n equals 1 to n equals 4. So we find this. Now we need to find the number of transition and the number of possible wavelength. So we have this. So I'm redrawing this. Okay, this is n equals 1 ground state, n equals 2, n equals 3, and finally n equals 4. So the hydrogen atom is in n equals 4. So we have this. Now we need to find the possible transition. Okay, so we can have this transition from n equals 4 to n equals 1. Next, we can have this transition from n equals 4 to n equals 2. And we can have this transition from n equals 4 to n equals 3. Clear? We can have this. Now, from n equals 3, okay, we can have this transition from n equals 3 to n equals 1. And from n equals 3 to n equals 2, we can have this. And from n equals 2 to n equals 1. So we can have these transition. So when we count the number of transition, okay, we find 1, 2, 3, 4, 5, 6. So what we find? The number of possible transition, okay, in going to ground state is 6. So I'm writing over here, okay. The number of possible transition in going to ground state, okay. Ground state is 6. So we have this. We have this, okay. So what do you find? Therefore, 6 different wavelengths are possible. So I'm writing, therefore, 6 different wavelengths or wavelength, okay, are possible. So from question, okay, we are asked to find how many different wavelengths are possible. So we find 6 different wavelength, okay, possible. So we have this. And next, we are asked to find the largest wavelength among these. Clear? And we know that for largest or maximum wavelength, okay, wavelength, energy is minimum. energy is minimum. So we find this. Clear? We find this. That is, we can write in this way. For largest or maximum wavelength, energy is minimum. So we have this. Now we know the energy corresponding to n equals 4, okay, is minus 0.79 electron volt. So this energy is minus 0.79 electron volt. So we have this, and ground state energy is minus 13.6 electron volt. Now we are asked to find the wavelength, okay, that is maximum wavelength, and the transition from n equals 4 to n equals 3 gives photon of maximum or largest wavelength. Okay, so I'm writing over here the transition from n equals 4 to n equals 3. Okay, so we find the energy difference for this transition is minimum. Okay, level gives photon, okay, photon of maximum or largest wavelength. So we have this. Clear? So in order to find the maximum wavelength, we must determine the energy corresponding to n equals 3. So I'm writing over here. For this, okay, let me write over here. For this, we have to find energy, okay, corresponding to n equals 3. So we must note this, okay. Now let us find the energy corresponding to n equals 3, okay. So we have to find this. So I'm redrawing the energy level, okay. N equals 1, this is ground state, and its energy is minus 13.6 electron volt. This is n equals 2. This is n equals 3, okay. And this is n equals 4. And the energy corresponding to n equals 4 is minus 0.79, okay. Minus 0.79 electron volt, okay. So we have this. And to find, so I'm writing over here E4, okay. So this is E4, okay. So we have this. Clear? So E4 is minus 0.79 electron volt. So we have to find energy, okay, for n equals 3. So we have to find E3, okay. So to find E3, we use this. En equals minus 13.6 electron volt by n square. Therefore, we can write E3 equals, okay, taking n equals 3. So we have minus 13.6 electron volt by 9, okay. So on simplification, we get E3 equals minus 1.51 electron volt. So we have this. So this is minus 1.51 electron volt. So as I said earlier, this transition, okay, this transition gives photon of maximum wavelength, that is photon of minimum energy. So we find this. Clear? We have this. Now we can write, therefore, we can write, okay, delta E. So this equals Hc by lambda max, and delta E is E4. We have atom, okay, de-excited from n equals 4 to n equals 3, okay, E4 minus E3. So this equals Hc by lambda max, okay. So we have this. Now we know E4 is minus 0.79 electron volt minus E3 is minus 1.51 electron volt equals Planck's constant is 6.63 times 10 power minus 34 joule second times C, and C is 3 times 10 power 8 meter per second divided by lambda max, okay. So we have this. So this cancels out, okay. So we have this. Now let us simplify, okay. So we get minus 0.79 electron volt plus 1.51 electron volt equals, now when we find this product, we get 1.9, okay, 89 times 10 power minus 25 joule meter, okay. We are finding the product in numerator divided by lambda max. Clear? Now let us simplify the left hand side. So we get 0.66 electron volt equals 1.989 times 10 power minus 25 joule meter by lambda max. Now we are going to find maximum wavelength, okay. So lambda max equals 1.989 10 power minus 25 joule meter divided by 0.66, and we know 1 electron volt equals 1.6 times 10 power minus 19 joule, okay. So we have to convert this electron volt into joule, okay. So I'm writing in this way, okay, directly 1.6 times 10 power minus 19 joule. So joule and joule cancels out, okay. So we have maximum wavelength or largest wavelength, okay. So this equals, when we do this simplification, we get 1883.52 times 10 power minus 9 meter. Or we can convert this, okay, in angstrom also, and write lambda max equals 1883.5.2 times 10 power minus 10 meter. So this is 1883.5.2 angstrom. So we have this. Clear? We have this.